Hello and welcome to the next session on algorithmic problem solving. In this session, we are going to solve the deletion from an array problem. The input to the problem is an array of integers and a user-defined key value v to be deleted. The goal is to design an algorithm which deletes all occurrences of v from A. The output is the modified array A with all occurrences of v removed. We need to pack A as far left as possible. Let us try out various simple approaches on the whiteboard first.
Array A, and with let us suppose the numbers are 3, 5, 6, 7, 7, 7, 7, then 8, 8, and 9 and 10. So since A is sorted, the duplicate entries will be huddled together. So the user defined K is equal to 7. And we would like to remove all instances of K. So the approach would be simple. So first we can, since it is sorted, we can binary search for A, for K in A. So that would be order log n time. And then we locate the first instance of occurrence of K in A. And then we subsequently, we remove the occurrences of K one after another. And then we record how many occurrences we have deleted, and everything else now goes back so many spaces, right? So for example, here we would record that we have deleted 4 occurrences of 7, and all the elements after 7, 8 onwards, they would be moved back 4 positions, right? So your AI would become AI plus M, where M is the number of occurrences of K. And this you would do for this location onwards. So if your I is the location, I is the index such that I is greater than or equal to j and less than or equal to n minus 1, where j is the first instance of occurrence of A, K in A. So this is clearly an order n time algorithm, because the binary search would take order log n time, but subsequent removal of the occurrences of the element K and subsequent movement of the elements backwards, subsequent elements backwards, overall would take order of n time. So this is an order n algorithm. So the next part of the question was that what happens if A is unsorted? So suppose K is 7, but this time, because the array is unsorted, the 7s are not huddled up together, they are scattered. Okay. So one option could be that we just scan through the array and keep removing the 7s as they occur. And then as they occur, we remove the 7s and shift the subsequent elements all backwards. So that's one option. So if you do that, so this would change to 8, 3, 10, 7, 6, 10, 7, 7, 5, 8, with the first 7 removed, first occurrence of 7 removed. And then subsequently, we scan the array further, and then we look at another 7, and then we remove the 7 and then shift all the elements after the occurrence of the 7 backwards by 1 unit each, 1 space each. So this becomes 8, 3, 10, 6, 10, 7, 7, 5, 8. And then again, we locate the next 7. And then, of course, we remove the last occurrence of the 7 as well. So it becomes 8, 3, 10, 6, 10, 5, 8. So this would take order n time for each removal of 7. So overall, it could take order n squared time, depending on where the occurrences of k are, in which positions they are, which could be anywhere. So this is an order n square algorithm. However, we can improve this straight away by sorting, right? So if you sort the array, then it becomes an order n log n algorithm because it takes order n log n time to sort. And then you can use the previous version of the algorithm where the array is sorted. And that would take order n time to remove the occurrences of k from the sorted array. So overall, it takes order n log n time. So with sorting, we can improve this to order n log n. Now let us see if we can do still better than that. So we have an array A, 8, 3, 7, 10. Seven, 7, 5, 8, and k is equal to 7, as in our example. So what we can do is we scan the array A and then keep copying the elements which are not equal to k to another array B. So this would be 3. And the 7 is not copied, 10 is copied, 7 is not copied. So 6, 10 is copied. Then the 2 7s are not copied, and 5 and 8 are copied. Okay. So this would take order n time to copy to another array B. And then if you want your answer to be in A, you can copy it back to A. So overall, you can do it in order n time. So this is order n time, but the overhead is the extra array that you use out here. So this is order n extra space. So mind you, all the previous algorithms that we talked about, they were all in place. Meaning extra space was order 1. So just for some maintaining some indices and things like that. So you did not need this array B. So with the array B, we can get the time down to running time down to ON, but the space requirement increases. Now the question is, can we do it in ON time with constant amount of extra space?
Let us summarize the different algorithms we have tried out so far. For sorted arrays, we can provide an order n time, order n space, in place solution. For unsorted arrays, we can either solve the problem in place in order n log n time. Else, we have a linear time solution which uses an additional buffer to solve the problem. So, a question is, can we solve the problem in place in linear time?
Consider this example here. We have the input array A equals 3, 7, 4, 16, 44, 7, 3, 33, 7, 26, 53, 7. We need to delete all occurrences of 7 to get the array 3, 3, 4, 16, 44, 3, 33, 26, 53. We initialize two indices rptr and wptr to 0. The index rptr is the position in the array from where we read. The index wptr is the position in the array where we write. As we scan the array from left to right, we will increment rptr and wptr, retaining their respective meanings. Since A0 is 3, we need to retain it in the array. We increment rptr and wptr and move on. Since A1 is 7, it is going to be deleted. We increment our PTR but WPTR does not change. The next red number is 4. It is written into A1. Both RPTR and WPTR are incremented. 16 read from A3 is written to A2. Again, both RPTR and WPTR are incremented. Next, 44 is written into A3. Again, both RPTR and WPTR are incremented. A5 is 7 which needs to be deleted. Hence RPTR is incremented but WPTR is not. Next, 3 is written into location A4. Then, RPTR and WPTR are incremented. Now, 33 is written in location 5. Both RPTR and WPTR are incremented. Next item read is a 7 at location 8 which needs to be deleted. Next RPTR is incremented but WPTR is not, since a 7 was last read. The next number read is 26 which is written into location 6. Then, both RPTR and WPTR are incremented. Now, A10 is written into A7. Both RPTR and WPTR are incremented. Since the 7 in position 8 has to be deleted, RPTR must incremented but not WPTR. But there are no more integers to read. We are done. The relevant elements remain in the first 8 locations of the array. Note that WPTR was always less than or equal to RPTR and this helps in achieving an in-place algorithm. The algorithm runs in order of n time and takes order n space. It is an in-place algorithm with no extra space required other than what is used for storing the data. Here we share a Python implementation. You may treat this as pseudocode for further implementation in other languages. The parameter k is the item whose all occurrences need to be deleted. The algorithm scans the sequence in a list from left to right, checking for each encountered integer if it is equal to k. When the current element is not k, both RPTR and WPTR are incremented. When an instance of k is encountered, only RPTR is incremented. Here is a question. What is the relationship between the indices RPTR and WPTR? Option A. RPTR less than or equal to WPTR always. Option B. WPTR less than or equal to RPTR always. Option C. WPTR greater than RPTR sometimes. Option D. RPTR equals WPTR never. Answer is option B. WPTR less than or equal to RPTR always. Another question. What are the time bound and the extra space required, beyond what is required for the input data, for the best algorithm that we studied for the deletion from unsorted array problem? Option A. Order, n, time, order, 1, extra space. Extra space. Option B. Order, n, time order, n, extra space. Option C. Order, n log n, time order, 1, extra space. Option D. Order, n log n, time, order, n. The answer is option A. Order, n, time, order, 1, extra space. Another question. Suppose the algorithm just described needs to be modified to delete from an input unsorted array A of m elements, all occurrences of all elements present in an unsorted array B of n elements, where n is much greater than 2 raised to the power of m. Which of the following would be asymptotically faster approach? Approach P. Sort B using an order, n log n, sorting algorithm and check each element of A and B by binary search. Or approach Q, leave B unsorted and use linear search to check for elements from A. Option A, P is faster than Q. Option B, Q is faster than P. Option C, both are equal. Option Answer, option B, Q is faster than P. P takes order n log n time, Q takes order n m. Here m is much smaller than log n.
Thank you. This course is brought to you by Elahay Technologies.